This is an example problem of a ball rolling down an inclined plane. So let's have an inclined plane of angle beta to the horizontal and a spherical ball of radius r and mass big M. And just a quick reminder that the moment of inertia for a uniform sphere is 2/5 times the mass of the sphere times the radius squared. You can look that up in the table of moments of inertia that will be provided on the equation sheet. Like we were doing in class, we need to, we're going to solve this first to find the acceleration of this ball in the ramp. We're going to use the Newton's laws approach. For now that we have rotating objects, our free body diagrams for mass M needs to not just be a point, but a sketch of the extended object. And this is important because it now matters where we apply these forces. So if we go down our checklist, I think there's, we are near the surface of the Earth, so there is a weight mg vertically down. The ball is touching a surface, so that gives us a normal force. The normal force acts at the point of contact, right? And that's normal to the surface, so that's 90 degrees. And we do need to have some static friction in this problem, mu sub s. An unknown for us, but we know that if the ball rolls without slipping, there must be some static friction. You can imagine maybe if this plane were greased up, then that ball would just slide down. So there must be some amount of friction to make it roll. So there must be some friction force that's opposing the motion, F sub s. Remember that in static friction forces, the F sub s, the force due to friction, is less than or equal to mu s times n. And we don't know that these two are equal to each other like we've been able to use in the past. Okay, so three forces are all that we have. So we can write a net force in x, net force in y equations. Let's choose some axes. We know that the balls are going to accelerate down the ramp, so we'll choose the axes like this. One of them in the direction of the acceleration. And then we need to, Fs is already parallel to x, n is parallel to y, but mg needs to be broken down into components. So I think that if we consider that there's 90 degrees between horizontal and vertically down, and that there is some angle beta here between the ramp and horizontal, then this angle must be 90 minus beta, and this must be 90 minus that, which is beta again. So if we break mg down into two components, like so, this one is mg sine beta, opposite, and this piece is mg cosine beta. All right, so in the x direction, net forces must be ax. This will be what we're trying to find. And in the y direction, though, we chose our axes so that there is no acceleration in the y direction. So may equals 0. All right. So for x, I see two components, the mg sine beta and fs. We've replaced this guy. So mg sine beta minus fs is equal to max. In the y direction, I see a normal force opposing, keeping us from going all, through the surface, and mg beta keeping us coming off the surface, or mg cosine beta. So n minus mg cosine beta is equal to 0. Notice that this formula, in the y direction, this tells us how big n is, which in the past, we've been able to use the normal force to find the static friction. But in this problem, we don't know that the static friction is just equal to mu times n. Right? So therefore, we can't use the normal force to find the static friction force. So we need some other approach. And that approach is going to come from considering the rotational motion of the ball and remembering that it's rolling without slipping. So our Newton's second law for rotations is that the net torque is equal to I alpha. So to apply this formula, we need to choose an axis around which we're going to calculate the torques. You can choose many different places here, but I'm going to choose the center of mass. I might draw one more diagram just so this doesn't get too crowded, so that we can choose an axis that goes through the center of mass, and I'll choose clockwise or in right-handed rule into the board as a positive direction. So there are three forces that might be providing torques here. We need to do the torque from the weight plus these are all vector quantities, plus the torque from the normal force, plus the torque from the friction force. These are the three torques we need to consider. And to find those, we're going to, each one, we need to find the moment arm, the radius vector, the position vector that goes from the axis to the place where this force is being applied. So the vector that goes from the axis to the place where the weight is, plus the position vector that goes from the axis to the place where the normal force, cross normal force, plus the position vector for where the friction force is cross the friction force. All right. So we need to do these three cross products. Note in the first one that the weight acts on the center of mass. So the distance from the center of mass to the center of mass is just 0. So this piece goes away. There's no torque due to the weight. And that'll be the same. There's never any torque around the center of mass due to the weight of an object. In this piece, we're looking for the torque due to the normal force. The normal force is being applied here, right? So this is R in from the axis to that spot. But notice that the normal force is anti-parallel to that, right? So this term becomes Rn, which is just the radius of our sphere, times the normal force, times the sine of the angle between these. But the angle here is 180 degrees. So sine of 180 is just 0. So this piece also goes away. So we're down to one torque. And for that piece, the position vector that goes from the center to the place where the friction force is again just the radius of the sphere. The friction force is now, we can just say Fs is what we call that friction force. And the angle between those two is 90 degrees. And sine of 90 is just 1. So this term survives, and we're left with Rfs is equal to I times alpha. Note, let's check the direction of this really quickly. If we do the right-hand rule, our whole arm in the direction of Rn, we roll our wrist until our fingers can flap in the direction of F, then my thumb is into the board, and so this is a positive direction for us, clockwise from this view torque. So alpha is going to be in the positive direction, which is what we'd expect. We'd expect for the ball to roll like this. Okay, so we know the moment of inertia for the sphere. We can plug that in here. And lastly, we can relate this alpha, the angular acceleration of the sphere, to the linear acceleration through the no-slip condition. Remember, we wanted to roll without slipping. So the no-slip condition, I like to remember, starts with the arc length, and then we take the derivative of position becomes velocity, and the derivative of theta becomes angular velocity, and then A is equal to R alpha. So alpha must just be A over R. Notice that the radius where the surface and the sphere are in contact is just the radius of the sphere. So I'm going to replace I with 2/5 mr squared, and alpha with A over R. So we can now solve for Fs, dividing the R through this R, that one, and these two all cancel. And this is just 2/5 MA. And this A is the same AX over there. Okay. I have a little bit of a notation problem. I'm going back and forth between small m's and big M's, but there's only one mass. It's the mass of the block. So maybe let's replace these big M's with little m's. All right, so now we've found the friction force is related to the acceleration using this angular piece, and that is what we're going to go back into here. So this comes in here, mg sine beta minus 2/5 max must be equal to max. We're going to solve for ax, moving these terms over there, so mg sine beta equals 1 max plus 2/5 max is 7/5 max. The masses all cancel, and we move the 7/5 to the other side, becomes a 5/7. So ax is 5/7 g sine beta. This is pretty interesting. If you remember, for a block that slid down a ramp, the block sliding, we got previously an acceleration equal to g sine beta. So this rolling ball should accelerate at a slightly lower rate. And but that makes sense, because here, when this was sliding without friction, in this problem there is some friction force that's going to oppose the gravitational force down the ramp and should lower the acceleration. Okay, so another part of this question we could ask is, how fast is the ball going when it gets to the bottom of the ramp? So V final is maybe something we could ask for. To answer that, we need to know maybe how far down the ramp is, or even easier, it might be we could just say how high up the ball started between the top and the bottom. So of course, now that we know the acceleration, we could use that, and knowing the initial velocity, we could use that to find the final velocity. Why don't we do that really quickly? If the ramp is has angle beta and height h, then this distance d, so the sine of beta must be equal to opposite h over d. Okay, and so therefore d is equal to h over sine beta. We said v naught was 0. We're going to find v final, and we have an acceleration that's 5/7 g sine beta. So let's see if we can't find that v final. I think a useful formula would be v final squared is v initial squared plus 2a delta x. So the distance as we go down the ramp was just h sine beta, and we started from 0. So v final squared is 0 plus 2 times 5/7 g sine beta times delta x, which we said was h over sine beta. And so it looks like v final then is equal to, we get 10/7 gh. The sine betas go away. So square root of 10/7 gh. All right. Those units look good. That's meters per second squared times meters. Leaves us with meters per second. Okay, I want to approach this problem, though, really quickly from a different perspective, using the energy principle. And one of the neat things about this is we can say that, remember that delta E, the change in mechanical energy, is equal to the work done by non-conservative forces. In this problem, we did have a friction force, but it was a static friction force. That point never moved, right? So therefore, in this problem, friction doesn't actually do any work, right? Because the displacement over which that force acted is 0. So we can just use a conservation of energy statement. This says that delta K plus delta U is equal to 0. The only kind of potential energy we have here is the gravitational potential. So, but we have two kinds of kinetic energy, which is important in this case. So we have our, this is K rotational final minus K rotational initial plus K translational final minus K translational initial. So this ball is translating and rotating. It has two kinds of kinetic energy. The gravitational potential is mgh final minus mgh initial, and those all must add up to 0. Initially, we were not rotating or translating. We started with v equals 0, and so therefore omega must be 0. And also, we'll choose h final to be 0. That way, h initial is just our h. So the formula for rotational kinetic energy was 1/2 I omega squared. And for translational, this is omega final, is 1/2 m v final squared. Subtract mgh is equal to 0. Now, we know I because it's a solid sphere. So I is 2/5 mr, big R, squared. And omega final is related to v final through the same set of no slip conditions, right? Because the ball's translational motion is related to its rotational motion because it's not slipping. So omega final must just be v final over r, quantity squared. So plus 1/2 mv final squared minus mgh is equal to 0. So we want to solve now for v final. Notice that each term has an m in it, so they all cancel. We can move the gh over here. On this side, I have 1/2 times 2/5 is 1/5. And the r squared here cancels with the r squared there. So this is 1/5 v final squared plus 1/2 v final squared. This must be equal to gh. If we go to tenths here, this is 2 tenths plus 5 tenths v final squared equals gh. And so v final then must be equal to the square root of 7/10 moved to the other side is 10/7 gh, which is, I think, yeah, that's just what we got on the other side. So these two approaches, an energy principle, which I think you can see is much, if all we wanted to know was the final velocity at the bottom of the ramp, it's much easier to skip straight to this piece. But if you want to know the acceleration, you'll have to go through this process. This process will also tell us how big, if you plug this A back in here, how big the friction force is, and could tell you how big the mu needs to be in order for this ball to roll without sliding, right? And to find out the minimum mu, you could actually use the equality part of this equation to solve for that. Maybe let's do that really fast. Minimum mu s required for rolling without slipping. To find that, we can use the equality here. So if it's the minimum, we're looking for the smallest. So mu s in. In we found earlier using the y component of the total force. So n must be equal to mg cosine beta. And fs we found earlier to be 2/5 max. And ax we also found earlier to be 5/7 g sine beta. So we plug all these pieces in. 5/7 times 2/5 is 2/7 mg sine beta. So 2/7 mg sine beta is fs. Must be equal to mu s times n, which is mg cosine beta. So solving for mu s, we get that it is the mg cancel on both sides, the cosine turns into a tangent, so it's 2/7 tangent beta. The tangent beta, you might remember the mu being related to the 2/7 has to do with this is required, what's required for a sphere with this kind of a moment of inertia. So okay.